from electrical engineering and control theory, which are mainly, what I'll be talking about is sort of material that's already known in those subjects. But the reason why I want to think about it a new way is because I find that when I'm looking at the diagrams that people use in biology and in ecology and other subjects, they often rely on simpler ideas which come from these subjects of human-made networks. And because electrical engineering and control theory have been studied for many decades in quite a mathematical way, it's much easier to just grab a hold of the ideas in those subjects than in biology and polish them up mathematically. So you should think of this as like a preparation for some future project for dealing with more complex systems. So this is a picture of a signal flow graph here on the bottom and a machine that it represents on top. So the introduction of category theory into the study of networks began in a formal way with quantum mechanics and quantum field theory, where they're focused on linear algebra, Hilbert spaces and operators, and in this somewhat simplified sense, you can say they're studying the category with vector spaces as objects and linear maps as morphisms, and then you can do two morphisms in parallel by tensoring. You can tensor to vector spaces and tensor to linear operators, and that gives you the structure of what's called a symmetric monoidal category, which I sketched in my previous talk. It's a concept well known to many of you. So Feynman diagrams you can think of as pictures of morphisms in this particular symmetric monoidal category, and mathematical physicists these days really take that attitude fairly seriously and use it to study things like topological quantum field theory, quantum computing, and other things. And the center here is full of a beehive of activity in those various subjects. But my claim is that although this is a great advance in taking category theory out of the ivory tower of pure mathematics and bringing it down into practice, it's still a bit of an ivory tower. Quantum computing and topological quantum field theory is still, I'd say, fairly removed from the hustle and bustle of ordinary applied mathematics. And so I want to bring category theory out into the town square and get it to work for more mundane but still beautiful things. And so it turns out that when you start trying to think about that, especially in the examples of electrical engineering and control theory, you see that there's another category that shows up right away, which is the same category, the category of vector spaces, but made symmetric monoidal in a different way, a simpler way actually, using direct sums of vector spaces instead of the normal tensor product. So in symmetric monoidal category land, we use the word tensor product in a very abstracted sense to mean any way of sticking together two objects that obey some axioms, and direct sum obeys those axioms. So today I want to look at how this somewhat sadly neglected symmetric monoidal category shows up. So it shows up in things like signal flow graphs. So control theory is the branch of, originally you could say, classical mechanics, which deals with open systems, with systems which interact with their environment. For example, machines that have knobs that you can turn and that push on their external environment. So it has a very different attitude than the classical mechanics we learn in a typical physics course, which focuses on closed systems, which are described by a Hamiltonian and do their thing without noticing the rest of the universe. So the whole point of open systems is that you can stick together open systems. The output of one open system can be the input of the next. You can put together machines to form bigger machines. And that's what category theory is all about, as I argued last time. It's about sticking together processes to get larger processes. So control theorists might describe this machine here where you turn a dial and it rotates this telescope. more abstract way using this signal flow graph where you adjust, the external agent, adjusts the parameter theta, the angle for the dial. That in turn affects various other parameters describing the internal workings of the machine, and then there might be a final output, which is the angle of this telescope, for example. But there are also various feedback loops where some parameter goes back and affects a previous one. And typically the way they will work in linear control theory is that some signal will be the sum or difference of two other signals that come in. So here you see a little 1 and a -1, if you can see the slides. That means that this function here is this one minus that one. Control theory has a classical branch which is focused on linear systems because, first of all, of course, linear systems are easier to study, and second of all, if you're working in control theory, you're trying to get a machine to behave in a way where it doesn't break, right? So when a machine breaks, that's typically a very nonlinear phenomenon. But within the nice range of operating parameters of a machine, that you can often describe its behavior in a linear way, not always, but linear control theory is based on that. And so if you're like have some people trying to design a chemical plant that's manufacturing some chemicals, and it's supposed to, when one tank gets too hot, you're supposed to cool it down. If the concentration of some chemical gets too high, you're supposed to lower it. That's the kind of thing people study using linear control theory, where you linearize about the optimal state, and then you try to adjust things to make it stay near that optimal state. So it's about linear algebra, but it's a particular sort of linear algebra which is done diagrammatically, and where the things you're adding or subtracting and multiplying by scalars are functions of time. So those I'll call signals. That's the standard term. So think of a signal as just being a smooth real-valued function of time. And I want to describe some little boxes, or little morphisms, you could say, that describe what you can do to a signal. So you can multiply a signal by a scalar, a constant, and get a new signal. And so I'll just write that scalar in a little triangle and have the triangle pointing down so that we know which is what's coming out and what's coming in. Even if we turn the picture upside down, we would still know who's coming in and who's going out. So one of the things we want to do with these signals is integrate them or differentiate them with respect to time. Control theorists often take integration as more fundamental. It's a more stable process to do. And so they would take this as a basic operation that you can do to a signal and get a new signal. So for example, a very simple machine is a rock sitting on a table or say, hovering in space with no gravity. So what happens when you push on a rock? Well, you exert a force, which is a signal, a certain function of time. I'm just looking at scalar valued things, but you could look at vector valued ones very easily. So a rock moving on in one dimension. So you divide the force by m to get the acceleration. You integrate that once to get the velocity, and you integrate that twice to get the position of the rock. So that's the sort of simplest second-order machine that you can build. And then when you have a whole bunch of things interacting in a more complicated way, we get much more complicated diagrams of this general sort. Now, integration introduces an ambiguity. There's a constant of integration. It's not really true that if you feed in a function and integrate it, that there's a specific antiderivative necessarily. But electrical engineers who study linear systems often try to get around that issue in the following way. Basically, by picking a particular antiderivative, they use Laplace transforms to write their signals as linear combinations or integrals of some special functions, namely exponentials, e to the minus st, exponentially decaying functions, and then they define the integral of this function to be just the sort of most obvious antiderivative of it. So then you do have a well-defined way of integrating a signal. So one thing they do, which is very nice, which is the Laplace transform idea. If you're an algebraist, you think of Laplace transforms in the following way. it's a way of turning integration into a special case of scalar multiplication. So I was talking about scalars, and you should have been imagining real numbers, but we can make a larger field of scalars by taking the real numbers and adjoining this extra variable s, which is what's showing up in this formula here. And you can get a field, that is something where you can add, multiply, subtract, and divide, if you look at all rational functions of s. So here we're seeing, we're taking this signal and we're multiplying it by 1 over s. That's another way to think about integration. So if you've ever studied electrical engineering, you'll see lots of functions of one complex variable. It can be often useful to think of s as possibly taking complex values, but that's not important in what I'm doing right now, so I'll just think of taking the real numbers and throwing in this extra variable s that has the meaning of differentiation, so that 1 over s has the meaning of integration. So we're doing linear algebra over a field, but it's a slightly more interesting field than just the real numbers. But because I'm a mathematician, I can't resist being general. So let's just say we have any old field. So think of this as the rational functions in one variable. And then for us, what a signal flow graph with some number of inputs and some number of outputs will mean is a linear map from some vector space over that field to some other vector space over that field. So if we have m inputs, we have the m-dimensional vector space as the input of this linear map, and outputs we map to that field to the nth power. So this is a black box. This could have all sorts of interesting things going on in it, like those little scalar multiplications and other things which I'm about to introduce. And I'll describe how to build up complicated machines, so to speak, out of those building blocks. But whenever we have any diagram with some number of edges coming in and some going out, it will represent some linear map like that. So if you want to make it sound like you need a PhD to understand this, you say signal flow graphs are pictures of morphisms in this category, the category of finite dimensional vector spaces over our field K. And we're going to make it into actually a symmetric monoidal category using direct sum. So that means when we have a bunch of wires and another bunch of wires next to it, that means we're taking the direct sum of two vector spaces. So k to the m, direct sum k to the m prime would give us k to the m plus m prime. So what we'll do is we'll build these from little generators, from simple machines. Build arbitrary machines from simple pieces. That's what people do in signal flow diagrams. I'm just saying it in a more mathy kind of way. So we have scalar multiplication, which I've already told you about. We can add two signals, so I'll use a little black triangle like this to mean addition. So it's addition of two numbers in our field to get another number in our field. This diagram is supposed to be asymmetrical enough so that even if you were standing on your head, or looking at it sideways, you could see which was the output. The output comes sort of straight out of a triangle corner, whereas the inputs go parallel to the edges of the triangle. So we may twist these diagrams around, but you're supposed to be able to see what's the input and what's the output of this addition operation. Third, we can duplicate a signal. If you have a signal coming in, you might want to make two copies of it and have them come out. The mathematicians call the duplication operation the diagonal map, because if these are just plain old numbers, the set x, set of numbers x comma x is the diagonal in the plane. So it's just one of the favorable blessings of God that this looks like a delta here, so it must mean we're on to something. So in addition, there's some other building blocks that may seem trivial at first, but are definitely good to have. One is that you can delete a signal. You can throw it away. So there's a unique linear map from the one-dimensional vector space to the zero-dimensional vector space. It just sends any signal to zero. And we'll just draw it like this. This should look a little bit like a wastebasket, because that's the idea. So if you've studied category theory and you know about categories with finite products, you'll know that those are categories where you can duplicate things and also delete them, and that duplication and deletion always go hand in hand. And I think it's really a profound fact that duplication and deletion fit together in a unified mathematical structure. And a great example of what I mean by this is if you go to a copying room, and every apartment has a copying room, right next to the Xerox machine is a wastebasket. So there needs to be both of those facilities to make your room into a nice category with finite products. For some reason, when people start duplicating things, they always wind up making things duplicated that they didn't want. And then you have to throw them out. So that goes hand in hand with duplication. But then, similarly, there's something that goes hand in hand with addition, which is 0. So addition, remember, had two things coming in and there's sum coming out. Similarly, there's this thing that may seem stupid at first, to have some source that emits the 0 signal, the function that's just 0 comes out. That seems sort of pointless at first, but you know, the Indians invented it, and we decided it was a useful concept. So finally, this category of vector spaces and direct sums, finite dimensional vector spaces is what I always mean here. It's a symmetric monoidal category, which means that you can switch two signals. There's a linear map called the braiding, which if you input f comma g, this ordered pair, out comes the ordered pair in the other order. And this braiding obeys some axioms that gives us a symmetric monoidal category. Then I won't write down the definition of that, since some of you know it, and the others, you can easily find it online, especially if you get my slides. You just click on that blue thing, and you'll get them. So these are our generators: scalar multiplication, addition, duplication, deletion, and 0. And it turns out that with these, together with the braiding, which is sort of implicit in the symmetric monoidal category, you can build lots of signal flow graphs, and in fact you can describe any linear map from any finite dimensional vector space to any other one out of these generators. So that's a theorem, which I'll say a bit more about. But the interesting thing is that these generators obey some unexpected relations. So one way to switch two signals is to just switch them, but there are other ways that aren't nearly so obvious, where you, for example, you take your two signals, you duplicate the first, you add it to your second, then you multiply it by -1, then you duplicate the second, you add it to the first, then you duplicate that, multiply by -1, and add it to the copy of that. If you work it out, it's a fun exercise to do, especially if you're really bored. You just write two numbers like x and y up on top here, and you just work out what happens, and by the end you get y and x switched. Okay, so yeah, I'll give you enough time to copy that down if you want to entertain yourself during the rest of my talk. So the point is that you wouldn't have instantly thought of this relationship, and so we're faced with the usual interesting question whenever you have a structure, an algebraic structure that is generated by some things, some elements or operations. You want to know a complete set of relations so that you can tell when two things in your structure are equal. So what are the relations that we need that we could hopefully prove these more subtle relations from? So that's what my grad student Jason Erbely at UC Riverside has worked out. Somehow or other, this should all be known, because the category of finite dimensional vector spaces and direct sums is not anything new, and none of these operations are terribly new. But I haven't really ever found a paper that presents this theorem. So we take these as our generators, and we'll say that this category is equivalent to the symmetric monoidal category, where you take these generators, stick them together any legal way to describe more complicated morphisms, along with the braiding, and then impose the following relations. So it's a generators and relations description of this category. And you're probably some of you are very familiar with that, some are more familiar with generators and relations descriptions of something like a group or something. It's the same idea. So here are the relations. They come in bunches. So the first bunch are all about addition and zero, and they say the expected things. Addition is associative. Zero behaves as it should. You add anything to zero, and it's the same as doing nothing at all. This is a picture of the identity morphism from the one-dimensional vector space to itself, not doing anything. And then if you switch to elements of your field and then add them, it's the same as just adding them. So mathematicians have a name for everything, and so they say this here gives you a commutative monoid. That's the name for those laws. Okay. Well, there's an upside-down version of all that stuff. Duplication and deletion obey the exact same rules upside down, and mathematicians use the word co to stand for doing things backwards. And so you get what they call a co-commutative comonoid. So this is one of the, this you could say is like the basic law of triplication. I guess bureaucrats like filling things out in triplicate. So you can take your form and duplicate it, and then duplicate the second copy, and it's the same as if you duplicated it and then duplicated the first copy. If you duplicate it, and whoops, you didn't need this one copy, and you throw it out, well, it's just duplicate it. And then finally, if you duplicate things and switch them, it's the same as not having switched them. That's sort of part of the fundamental idea of what makes them to be called duplication. They're the same. Okay, well that's nice. But then the monoid operations and the comonoid operations that fit together in a beautiful way. They obey these laws that some people are very familiar with from studying Hopf algebras or bialgebras. So here, this is the most exciting one, the top one here. It's the relationship between addition and duplication. So if we add two numbers and then duplicate the answer, it's the same as if we duplicated each of those numbers, switch the middle two, and then add the first two, and then add the second two. So this is the exciting axiom in a bialgebra. And then they're sort of less exciting. So it's the axiom that expresses the compatibility of, in our case, the addition and the duplication. But then there are less exciting ones that tell you how zero and duplication work, and dually how addition and throwing something away works. And then this is the most degenerate one of all. It says that if you take the number 0 and you throw it away, it's really not much of anything. So this is a diagram over here that's very hard to see. It's the map from the zero-dimensional vector space to the zero-dimensional vector space. So there's 0 wires coming in, and there's 0 wires coming out. And there's only one such map, so I might as well draw it in a way that saves ink. And so this is a sort of more complicated way to describe that map. So here we're saying that if you take the number 0 and duplicate it, you get 2 zeros. Here you're saying that if you take two numbers, add them, and throw the answer away, you might have just, well, thrown them both away. If you like fancier mathematical ways of describing things, you will know that these laws here say that the comonoid operations are monoid homomorphisms. They get along with the monoid structure. But then you can also turn that statement on its head and say it another way. You can say that the monoid operations are comonoid homomorphisms. Those are equivalent statements. But anyway, those are just different ways to think about this. There's more. We haven't even talked about scalar multiplication yet. And these axioms here concern scalar multiplication. That's what this triangle means here. And they say that the ring structure of our field K, that is multiplication, addition, 1, and 0, can all be recovered from the generators, from the other operations. So, in other words, for example, to multiply something by the product, BC, is the same as to multiply it by B and then by C. multiply it by a sum is just the same as to duplicate it, multiply one copy by B, the other by C, and then add the answers. So we're eliminating addition in the scalars for the addition operation as one of our generators. Multiplying by 1 acts as the identity. Multiplying by 0 is the same as throwing something away and then picking a 0. So this sort of lets us not have to mention times, plus, 1, and 0. We can eliminate them if we want. And there's a little bit more. One thing that we haven't gotten around to is that scalar multiplication is linear. It's compatible with addition and 0. So if I have two signals and I multiply them both by some number and then add them, it's the same as if I added them and multiplied them by the numbers. That's the distributive law. Similarly, multiplying 0 by any number is 0. So we're almost done, but because all of this formalism has a kind of vertical reflection symmetry, you should expect one more slide where we take this slide and turn it upside down, and that's it. So I've never heard anyone use the term collinear, but I just thought it would be fun. So scalar multiplication is also collinear, which means that it's compatible with duplication and deletion. So if you take a signal, duplicate it, and multiply each copy by C, it's the same as first multiplying it by C and then duplicating, or multiplying by C and then throwing something out. It's the same as just throwing it out. So that's the complete set of relations. Yeah?
Don't need a sort of Hopf or antipody axiom as well.
For negation or for...
Right, for the -1.
I haven't... Am I supposed to know how to draw? I don't know. I've never thought too much about drawing that, but that better follow from what I've said, or else this theorem is wrong. So afterwards, remind me to draw this extra law that you're talking about, and either derive it myself or make my grad student derive it, which just sounds even more fun. Yes?
So you just go one step back to the one for scalars. No,
That?
sorry, 2 steps back. Yeah, that.
Yep. Sorry?
It probably follows the antipodal one probably follows.
It's
from
got to
one
follow
on the
from
right.
this one. This is the one that says that
Yeah.
1 minus 1 is
Yeah,
0. So
yeah.
that's what I'll have to use.
Yeah.
I'm not fast enough. You already derived it? Okay.
Yeah.
Well, I'll still make my grad student.
Yeah,
I'll seem smart. You'll have to do more work. So that's part of what's going on in control theory. But there's something really crucial that I haven't talked about, which is in some sense the most important thing, which is that control theory has this idea of feedback loops, where you take an output of some machine and you loop it around back in, perhaps after processing it a bit, and feed it back into your machine. So here is sort of the general concept of control theory. You often see a version of this picture in an introduction to control theory. So the idea is you have some setting, some knob that you, the user, turns. First ignore the feedback loop. And you might send it into a controller. Here I'm just thinking about a single signal, but you could also have like a whole bunch of signals coming in if it's more complicated. The controller would apply some linear transformation to them and then feed information to the actual system, the machine that's really doing all the hard work. And then the machine would put out the output. But very often what happens is that machine will be unstable in some way or another. You could have this, remember, it could be a linear transformation of a signal that could involve derivatives and integrals. So what we're really doing here is we're solving a differential equation based on some input signals. And if you do certain kinds of differential equations, you'll run the risk of instability. So you're like trying to set the temp. You say like, I want to make my room warm, so I'll turn on the heat, but then the heat will just like keep coming on and on and on, and we'll get hotter and hotter, and that's not what you want. So what you do is you take a measurement of the system. In other words, you take some of the output of the system and feed it back into some sensor, for example, a thermostat, and then the output of that perhaps could be, this -1 is not really necessary, but sometimes what will happen is that you will subtract something and then feed it, and then add it to your initial setting, feed it back in. So a normal thermostat is not a linear device. It flicks between being on and off, but you can make a linear version of that, which when the system got to be too hot, it would just start pushing the knob on the temperature down and cool things down. And there's a whole elaborate theory of how you build the sensor and the controller to make a given system behave in a stable way. That's sort of the bulk of control theory, how to take a machine that does approximately what you want it to do but may go wild in various ways, and how you put it in a context that keeps it nice and stable. So the feedback loop idea is crucial there. And when we get to more sophisticated things, which we won't do in this talk, but when I, in my research, get to more sophisticated things like biology and ecology, the idea of feedback is crucial. As you know, if you've ever tried to manage an organization or even yourself, you know that feedback is crucial to keep things from running off the rails in different ways. So that's, and biological systems, they're full of it. So we need those. We need those extra abilities. And those extra abilities are hidden in here and here. These are the only two things that I haven't discussed. Those two little bends in the wire are the remaining thing I need to think about. So as I just said, feedback's the most important concept in control theory. And so you need wires that bend back somehow. You want to feed in a signal here and have it come around back out there, going backwards in time, so to speak. Or conversely this way. These aren't described by linear functions. There's something more general. They're linear relations. So now I'm going to introduce a larger category than the one I talked about that has these extra ingredients. So what's a linear relation? Well, it's a very simple thing. It goes from a vector space to another vector space, but because it's not a function, I need to give it some other weirder shaped arrow so you don't get mixed up. So I'll give it like a wiggly arrow, so it's a little dodgy. So it's a linear relation from a vector space to another vector space is just a linear or vector subspace of their direct sum. So that's just a linear version of the usual concept of a relation between sets, right? A relation from a set S to a set T is a subset of the Cartesian product of those sets. In other words, it's a set of ordered pairs. The pair, the first guy is related to the second guy if they're in that subset. But the direct sum of vector spaces is the Cartesian product, so this is really the same concept, but in a linear setting. And just as you can compose linear operators, you can compose linear relations. Get new ones. So if I have a linear relation from U to V, another one from V to W, I can define their composite, G composed with F, going from U all the way to W, in exactly the same way that I would define it for functions. Remember, a function is itself also a set of ordered pairs. So here we say that U comma W is in this subset, G composed with F, if there's some guy V in the vector space V, such that U and V are related to each other by the first relation, and then V and W is related by the second relation. So some of you, I know, are thoroughly knowledgeable about composition of relations, but for some reason relations have gotten really, have been really undervalued compared to functions. For some reason, when you teach people math, tell them a function is a set of ordered pairs, and then you like quickly move on to only talking about functions and no other sets of ordered pairs. And that's a terrible, terrible thing, especially because in real life, our relatives are in fact relations, right? So they're not functions necessarily. There's no function son of, right? But it is a relation. And so you're denying the ability to apply math to lots of important concepts when you focus on functions and not relations. So if you think about it in that very genealogical kind of way, then I hope this becomes clear if you've never thought about it before. So for example, there's a relation father of, and there's a relation mother of, and if you compose them, you get, I guess, paternal grandmother of, right? So she is my paternal grandmother if there's someone who is my father and her daughter. So that's just that. So when you have a linear function or a linear map, if you want to show off, it's a special case, namely the graph of that map, the set of pairs u comma phi of u. And then composing linear maps becomes a special case of composing linear relations. So we're taking our category of maps and embedding it in this larger category of relations, which I feel embarrassed mentioning this because there's some people who have known this probably before I was even born, or certainly before I knew any math. So there's a symmetric monoidal category which I'll call fin-rel K, as opposed to fin-vect K, with finite dimensional vector spaces as the objects, just like before, but now linear relations as morphisms. So it includes our previous category. And I want to argue that the fully general linear, we're only doing linear things, so I should say, fully general linear signal flow graphs are pictures of morphisms in this larger category, and typically our field is the one I talked about, the real numbers with this one extra variable that acts as differentiation. These are rational functions and one variable s. So let's see a little bit about how that works. So Jason has shown that besides the generators we've already seen in fin-vect, you only need two more to get all the morphisms in fin-rel. And those are these ones that I was hinting at, called the cup, is it shaped like a cup, and the cap. So these linear relations are relations that say that when a signal goes around the bend, the signal coming out has to equal the signal coming in. So they're not functions. In fact, here there's nothing interesting coming out, just because this is the zero-dimensional vector space down here. And here there's nothing interesting coming in, but they're interesting as relations. So a little more formally, the cup is a linear relation from k plus k to the zero-dimensional vector space. So that means it's a set of ordered pairs consisting of an element in k plus k and an element in the zero-dimensional vector space. So in other words, it's a triple. But it's not any old triple, it's a triple where the first two guys are the same. So any triple of that sort will be in this relation. So it's just a relation that imposes that the two inputs be equal, that makes them, forces them to be equal. And then similarly the cap is sort of the upside down version. So it will be a subset of 0 plus k, and it consists of triples where the second two, the latter two, are equal. So the two outputs can be anything at all, but they have to be equal. This is the kind of cool stuff you can do with relations that you can't do with functions. So this category, fin-rel K with direct sum, is one of these kind of symmetric monoidal categories that people in this building love. If you walk around, you'll see posters on the wall like advertising the virtues of dagger compact categories. And so that phrase there includes a bunch of properties. The most, so I don't want to go into it in detail, but the compactness amounts to an identity that holds for the cap and the cup, which is, for starters, this. So here what I'm doing is if you think about slicing it this way, I'm composing the identity tensor the cap with the cup tensor the identity, and that's just equal to the identity. But what it means is something very simple. If you send a signal around a wire and it wiggles around and comes out, it's the same thing. So you didn't need the wiggle in the wire. It doesn't do anything. This is the fundamental law of electrical engineering that says you can straighten out the darn cables and it still works. Right? The same way. So I call this the zigzag identity, and I call the second one the zag-zig. You want to have names for all your so this property makes you have what's called a compact category. The dagger aspect means that you can take any picture and you can flip it vertically and get a new picture. And we've already seen that a lot in all these kind of relations. So here are some things that are true. If I flip it upside down, and as part of flipping it upside down, what I mean by that is that I will let's see, I have to be a little careful here. I just realized that this could be even more subtle than I thought. So when I flip this black box upside down, what do I get? Well, you could get a white triangle. That way of defining what you mean by flipping things, where black turns into white as part of the flipping, that probably makes it into a dagger category. It's just a category where you have that ability to do that. It's obeying some sort of obvious axioms. But actually, now that I think about it, it's really bad to think when you're giving a talk. But I can't find the eraser.
It's on the board.
Ah! Look at it there. Are you running out of electricity?
Illustrate that big.
Okay, use the zag-zig identity. So there is also another way to think about turning things upside down. So here's the morphism for adding two signals and having one come out. We can, and Jason does, make up a new operation. It's an upside down version of that, which he draws as a black triangle. And the way he defines that is he just takes this thing and he turns the inputs into the output and the output into the input. So you can turn things upside down in this other way, and this is different. This is not duplication. This is what I would call co-addition, which says that it's a relation. It's not a function. It's a relation that says if you have some signal coming in and two signals coming out, the relation holds that the signal coming in is the sum of the two signals going out. So it's like addition, but read up from bottom to top. So that's different than duplication. So I just realized that this way of flipping things upside down may also give a dagger category. Just a different way of flipping things upside down. I'll need to think about that a bit more. So anyway, we definitely have a dagger compact category, but all of a sudden I'm worrying that we have it in two different ways. Even better. But Jason has proved a theorem which I won't fully state, which says that you can get all linear relations from these generators, where you now also include the cup and cap. And in addition to the relations that I wrote down, you've got some more. But I'm not going to tell you what those are, because I want to tell you about something else. But anyway, he's worked out what they are. So I want to spend the remaining little bit of time to tell you about some further directions. Well, one thing I haven't even really begun to grapple with is nonlinear versions of control theory. So I'm focusing on the diagrammatics, focusing on the aspects of thinking about signals as moving along wires and signal processors as morphisms. And that will have a nonlinear version, which will be much more complicated, not less algebraic in flavor than the linear version. And nonlinear control theory is incredibly important because while things like resistors, inductors, and capacitors are made to be linear, you try to make them be linear, there are all sorts of really crucial circuit elements like transistors, which are nonlinear, and that's very important these days. But anyway, in both the linear or the nonlinear version, there's a general question of how do you build devices that actually implement a given signal flow graph. You could build a circuit, which is some kind of diagram of its own, and try to get the circuit to do something when you feed in some currents into one end. You might want some currents coming out the other end that are functions of those coming in. So this is not a signal flow diagram, but it's supposed to somehow be the kind of diagram you draw when you're trying to build a machine that implements a signal flow diagram. So Brendan has been working on this, and there's a category, in fact something a little fancier, a bicategory, whose morphisms are circuit diagrams, and we're focusing on the linear case to get started. So we look at circuit diagrams made of resistors, capacitors, and inductors, which are some of the main linear circuit elements. We should do transformers too. But thanks to the work he's busy doing right now, while he's also videotaping me, he's multitasking. We know that there's a functor from that bicategory. Don't worry about the bi just yet. If I have time, I'll explain it. To the one I've been talking about, Fin-Relke, the one with the signal flow graphs. So the idea is, in theory, fairly simple, although as always things get more complicated when you try to work them out. So let's think of the simplest electrical circuit in the world, just a single resistor. You can think of it as having two inputs, the current and voltage at one end, and the current and voltage at the other end. Now, it's not true that these two are a function of those two, but there is a relation between, a linear relation involving these two and those two, and it depends on the resistance of your resistor. So there's some positive number called the resistance, which is involved in these relations. And these relations say, what do they say? Well, first they say Kirchhoff's law holds. The current flowing in is the current going out. And secondly, they say that the current at either end is the change in voltage, there's a sign convention here, divided by the resistance. And so there's a linear, these are picking out a two-dimensional subspace of the four-dimensional space span, whose basis vectors are these guys. So this is a linear relation. So what linear relation is it? Well, it should be some linear relation that we can draw using the notation that I've been introducing. I said you can get any linear relation that way. So there should be some signal flow diagram that you can draw where the signals I1 and V and V1 are coming in, and I2 and V2 are coming out. And then inside here, what you're doing is you're just using all these kind of building blocks that I was talking about, these guys here. And it's fairly easy to see what it is, if you think about it the right way. So we want I1 to equal I2, but then we want to use I1 for some other purpose as well. So I'll duplicate I1, and I'll pass one over to here, so that makes I2 equal to I1. And then here, well, I think the way it works out is that if I solve for V2, I get Ri1 plus V1 is V2. So what I'll do is I'll take this copy of I1 that's come out of here, I'll multiply it by the resistance, and then add it to V1 to get V2. So that's the simplest signal flow graph that you can draw that corresponds to this resistor. And so this is an example of this functor, which sends this morphism in the category of electrical circuit where the morphisms are electrical circuit diagrams, over to this morphism, which is what it does as a signal flow graph, how it turns signals into signals. So that's the idea of this functor here. That's an example of this functor here. So it says, for any circuit diagram, how the voltages and currents on the input wires are related to those on the output wires. Now the interesting thing is that you don't get all linear relations this way. So if you've got the space of voltages and currents on n wires, it's k to the n plus k to the n. But the interesting thing is it's not just a plain old vector space. It really is a symplectic vector space, meaning that it has a skew-symmetric pairing, a skew-symmetric non-degenerate bilinear form, where you form this number I1 dot product V2 minus I2 dot V1. That's it. Skew-symmetric, meaning if you switch these two guys, you get a minus sign there. And this is really mathematically the same as how in classical mechanics, if you take the space of all positions and momenta of a bunch of particles in a Euclidean space, that's also a symplectic vector space. You have a bunch of numbers for positions and a bunch of numbers for momenta, and this mathematical structure turns out to be really important in writing down things like Hamilton's equations. And so it turns out that the linear relations that we get from a circuit is always what's called the Lagrangian relation. So here are the voltages and currents coming in, here are those coming out. The circuit will pick out a linear subspace of the direct sum of those two vector spaces. But this is a symplectic vector space, and that's a symplectic vector space. So this whole thing here is a symplectic vector space, and there's a really nice kind of subspace of such a thing, of a symplectic vector space, called a Lagrangian subspace. And it's one that's on which this symplectic 2 form that I wrote down before is 0 when you restrict to that subspace. And more precisely, it's a maximal one. And that's also very famous in classical mechanics, at least if you get into it deep enough. You see that if you look at the, if you do the same kind of thing and you let these numbers be the initial positions and momenta of a bunch of particles, and those be the initial momenta and positions of a bunch of particles, typically would be the same number of particles in that situation. So before and after some period of time, a relation must hold relating those if you have solved Newton's law or Hamilton's equation or something. And so you get a certain subset of possible, you get a certain subset of this space, which are the allowed possibilities. It may not be linear, we may not be doing linear classical mechanics, which would be sort of boring, but so we'll get a submanifold, and it will be what's called a Lagrangian submanifold. So it's a submanifold such that every tangent space of it is a Lagrangian subspace of this thing. So that's something that, that's why people care about Lagrangian subspaces, really. It's because of their role in describing time evolution in classical mechanics. But here we're seeing it showing up in a different way. We're showing it that this before and after here is not really a matter of time, it's a matter of input and output of an electrical circuit. So there's a nice relationship going on here between control theory with its signal flow diagrams, electrical engineering with its circuit diagrams, category theory that lets you see that these are really both, that those kind of diagrams are morphisms in a category and there's a functor from one to the other. And then finally symplectic geometry, which says that the control diagrams, the control theory kind of diagrams you get are not arbitrary ones, but only those that get along with the symplectic structure. And that will become much more interesting in the non-linear case. And I think that this is something that I want to keep on working on for quite a while, because I mentioned before that there are these biological diagram languages that people use to describe how concentrations of chemicals affect other concentrations of chemicals. And people are already beginning to blend those ideas with the ideas of control theory. People are starting to do things like design synthetic organisms that do particular chemical tasks, and they're using ideas from control theory to try to make those organisms actually do what you want and not run off the rails by producing too much of some chemical and killing themselves off or something like that. But besides just for something like biotechnology, I think for understanding ecosystems and the stability of ecosystems, this kind of math would be nice. Yeah, so I'll stop here, and if no one can think of a question, I'll say why I said by category, but otherwise I won't. Okay, thanks. Someone should think of a question. I'll tell you later.
No, come on.
Okay, yes?
It occurs to me that you're handling causal structures in one sense, and in the relations, that sort of goes out the window somehow. And it feels like sort of looseness in that. And it seems to me if you want to get to rigor in these things, there's also a problem sort of linked to that, which is about what happens to the constructs as you go to the limits of high frequencies. I mean, that's a real problem in ordinary engineering. And yet it's sort of not mentioned in these things. It would appear to me that there are further, I guess, theorems to be applied to some of these components that will deal with this. And I'm particularly interested in whether some sort of change in the approach, like Browerian intuitionism or something, can help get those things focused better. Have you got any ideas on that?
So there are endless refinements to be made. So one that you mentioned is that when you have electrical circuits operating with signals of low frequency, they behave in a fairly simple way. For example, inductors, resistors, and capacitors just obey simple laws like this. But then when you start boosting up the frequency of your signal, the actual amount of time it takes for the information to get from one end of the circuit to the other actually matters. So I'm definitely not considering that. And there's a big branch of electrical circuit theory where you say we're not going to consider that because we're going to design machines to be operated under conditions where that doesn't matter. But as you start boosting up frequency so that time considerations matter, then what you're doing is you're revealing that these electrical circuits and this mathematical modeling here is really just an approximation to Maxwell's equations, where you have electromagnetic waves moving around limited by the speed of light. And there are people who definitely try to bridge the gap between the full-fledged differential equation point of view of Maxwell's equation and this sort of discretized point of view of electrical circuits. So one thing, for example, that a lot of practical electrical engineers do is what are called finite element methods, where you take space and time and chop it up into a lattice, and you do this for numerically simulating Maxwell's equations. So you have like electric fields and currents along edges in a lattice, and then as the lattice approaches the continuum, the problem approaches the partial differential equations of Maxwell's equations. So that would be very fun to think about from this point of view, because the lattice can still be thought of as a network, but then you'd be then in a position to study how a network description of something can actually sort of, as you refine the network ever more, can approach a continuum description. But it's definitely different than what I'm doing here, because there you would actually be caring about the amount of time it takes for a signal to pass from here to here, which is not incorporated here. So that's something that I definitely can be done, because in some sense the engineers have already done it, and it's a matter of making it nicer for me, making it more mathematically nice. I don't think any really sophisticated or novel math like intuitionistic logic is needed to think about that kind of thing. But a lot of linear algebra, basically, a lot more sophisticated linear algebra. So that's my answer to that so far, I guess. But that means I have a lot of work to do. Yeah.
When you have nonlinearities, for instance, a component saturates, doesn't that break the symmetry you were speaking about in the background?
I don't know of that. There's a lot of as far as I know, there should be a lot of nonlinear components that would still pick out. So it would not, if you had a nonlinear component, it would be picking out some subset of the space of currents and voltages on all your terminals. And I think in many cases that would still be what's called a Lagrangian submanifold of that. But I haven't gotten enough into this, so do you know of something like that? That there's like certain nonlinear elements that like ruin Lagrangianness? Yeah, the reason why I'm fairly optimistic is because I know that you can write down any nonlinear formula like Newton's law, F equals ma, where F is some nonlinear function, and then solve, well, find the solutions that relate the initial and final position and momenta of a bunch of particles, and you'll get some submanifold of a vector space of this sort, and it will always be Lagrangian. So nonlinearity doesn't kill that off, at least in that context.
And the bicategory?
And the bicategory. Okay. So the bicategory stuff is sort of the secret next level of things here. So when you draw some, well, I don't want to draw. When you draw a relationship like that weird relationship I wrote down, any of these actually, but let's just pick this weird one. So these are equal as linear maps, but if you're designing a signal flow diagram to accomplish a specific task, and someone tells you, design one that switches two signals, you probably get an A if you did this one, and you probably get an F if you came up with that one, right? There's something worse about this. It's too complicated. So although they're equal in the process they accomplish, they're different in some other way. And so what that suggests is that we should make up a bicategory where the one morphisms are these guys, and then the two morphisms are ways of going between these guys. And if you do that, then these different relations that I'm writing down, for example, you could say, okay, I'm going to make it be that I'll think of these as two morphisms instead of equations. So processes of turning one signal flow diagram into another. And so electrical engineers actually do think about that kind of thing. There's like there had been a whole industry of trying to find the minimal realization of an electrical circuit. It's the simplest one. So I think that will be really interesting. And basically the idea is, to me, that just amounts to taking these diagrams seriously as things. So as soon as you take a diagram seriously as a thing, then what thing means in mathematics is an object in a category, and so there should be morphisms between them, and that's what these are really pictures of. So we definitely do want to take these diagrams seriously as things, because they could be things like machines or biological systems and so on. And they could, yeah, so that's where the bicategory aspect comes in. And so, so my students Mike Stay and Alex Hoffnung have shown that in general, for any sort of way of labeling graphs, labeling their edges and vertices with labels, you get a bicategory where the one morphisms are these graphs with labeled edges and vertices, like these. And well, the simplest bicategory has the two morphisms just being isomorphisms. So graphs can have symmetries. So you get a bicategory that way. And then Mike Stay showed that that's a compact, closed, symmetric monoidal bicategory. So all that just is a way of saying that whenever you consider any of these kind of diagram languages where you draw diagrams as graphs, there's this compact, symmetric monoidal bicategory of those diagrams. And so then you're able to really think of those diagrams as things. And then there's a functor from that down to what those things mean. In other words, for example, there'd be a bicategory where the morphisms actually are these pictures, and then there'd be a functor from that down to the category of these finite relations, which what these pictures mean. So that, I think, is a place where higher category theory can really come in handy. Before, people were not really very clear about distinguishing between these diagrams as sort of just notation for something like linear operators or linear relations, and between thinking of them as actual machines. But of course, the interplay between thinking of them those two ways, that's what's the whole point of the subject. You build a machine in order to accomplish a task, but the machine is not the same as the accomplishment of the task. So that's what I want to be able to talk about in a precise way. Yep.
Sorry, very quickly, if there's time, can you just help me out? I was confused by the introduction of, you were talking about the cup and the cap.
Yep.
And the just relations, or in particular, they've got either two inputs and no output, or two outputs and no inputs.
Right.
I mean, intuitively, I was expecting when you said, oh, we're going to talk about these curves here, I was expecting to say, oh, well, they simply redirect in a causal way.
No, there's no cause. Yeah, that was the other thing. So he mentioned causality, and he mentioned causality. There's no particular causality in these diagrams. You can make up other formalisms, but when I have this cup here, I may have said the signal coming in here is equal to the one coming out there, but I could have equally well said the one coming in here is the one going out there. The coming in and going out aspect, like which way the signal is moving along the wire, plays no role in this setup at all. It's just that along a wire you have a signal, you have some function of time that you can measure when you're standing at a wire. You can measure, for example, the current at a point along the wire.
So
And we don't talk about, sorry?
As long as you don't get a causal direction problem coming towards you, sort of.
You don't, you can get, you don't get any real problem. You can get some interesting things that may look like they're problems, but then actually turn out to be great. So, for example, you could do something like this. So I could draw this signal flow diagram, and then I could try to think about what it means. Okay, so a signal is coming in. I don't know what this is yet, so I'll just call it G, okay? And then it's getting added with F, so this is F plus G. I'm supposed to have drawn this triangle clearly enough so that he's noted that that's the way addition is going. Then here I'm duplicating F plus G. So now I know what G is. It was F plus G. And then F plus G is coming out. So you could try to build this machine, but you'd see that something rather funny was going on. Because, well, what happens? So, can someone tell me the resolution to this paradox here?
There is no spook.
There is no what?
There is no
spook.
spoon.
Spoon? I have no idea what you're talking about. No, come on.
It'll be empty. It's an existential quantifier.
You can prove that f equals 0 from that equation, right? So in other words, there would be no way for this machine to accept any input other than 0. That means that it's definitely not a function, but it is a perfectly fine relation. So f is equal to 0, and what is g? I guess I haven't thought about this too much, but it looks like any g will work. Any g is allowed. So f is 0, g is arbitrary. So we're just picking up the subspace 0, g sitting inside k plus k. So this is not a machine you want to try to build at home, okay? But the point is that you can build machines that have some kind of seemingly contradictory behavior like this, but the formalism doesn't explode. The formalism just tells you, sorry, Buster, this is not a function. You can't stick in any signal you want and figure out what will come out. If we modified this a little bit, which people often do, then you do get machines that really do give you functions. So a very common kind of thing would be to have this come out and then multiply it by something like, say, -1/2. Then I'll let you work it out. Then you actually do get a function where you put in some, this does describe a linear operator. You can put in anything and then something well-defined will come out. It's just that when this number I've stuck in here is equal to 1, it gets some kind of blow up. But it's okay. Yeah. So I don't know if I answered your question, but I was trying to show you that there's no notion of causality here, and that really is in accord with a lot of traditional signal flow diagrams. They don't really need causality. You just need to know what signal you have along the wire. And in situations where it may seem to cause a problem, the formalism lets you know that something strange is going on, but the formalism is still perfectly consistent.
Yeah, and yet though there is definitely a notion, a causal explanation that one could apply to electric circuits. Whether that's valid or not, I don't know. But there's this discrepancy.
You have to be very careful about that. For example, even with a resistor, do I think of the current as causing the voltage difference, or do I think of the voltage difference as causing the current? Under certain circumstances, you might want to think about it one way or another. And that would probably have more to do with the apparatus you surrounded the resistor with than with the resistor itself. The resistor doesn't know who's causing what, right? So it should not be built into your description of the resistor itself. But anyway, I agree that it's a very interesting issue. There's a whole literature on what are called bond graphs, which is yet another formalism for describing electrical circuits. And they have this mysterious, to me, thing they call the causal stroke, where you draw some diagrams. It all seems to make perfect sense to me, but then you say, oh, but I want to know which thing is causing which, and so I'll draw an extra little arrow that means that this is causing that. And I haven't fully understood that. It seems at first silly to me because it seems to me like they can just sort of stick that on at the last minute and it doesn't do anything. But it's probably because I don't completely understand it. So it's related to, I mean, you could, if I wanted to ponder it, I would just think more about this resistor, very simple problem. You know, I could think of a resistor as a device for turning voltage differences into currents, or I could think of it as a device that turns currents into voltage differences, and I would notate it differently with this causal stroke. But I'm not really so sure yet if that's really essential, or if it's maybe just essential for our way of thinking about what it's doing. It's an interesting question.
Any more questions? If there is
well, we can quit and I'll still be around.
Yeah,
sure.
Okay, all right. So let's thank John very much for it. Hopefully see you all next week, same place, same time.
Next, chemistry. Take over chemistry.